Hello everyone, Galen here, and I'm going to be talking about your next lab, which is going to be motion in 2 dimensions. Just building upon what we've done the last couple of labs, you've done motion in 1D and acceleration in 1D, which is just basically along one axis, which you consider to be probably like the x-axis. So you had a x versus time graph that you looked at, and you had the acceleration or the velocity versus time and the acceleration versus time graphs. Well, now we're going to change this up a little bit. We're going to add another axis. So now we'll be looking at a motion in 2D, which, let's see here, is motion within a plane. So like I said, it's going to be like the XY plane, or maybe the XZ plane, or it could be the YZ plane. But it's going to be within one plane, so it makes it a little bit easier to deal with. Parabolic motion, oval-shaped motion will be two of the types of motion you'll be looking at today. Our objective for this lab is to examine the acceleration of an object that are moving in 2 dimensions or in a plane. Here we have the definition of acceleration, which is your change in velocity over your change in time. This is something that you should have seen over your last lab. There we go, change in velocity, change in time. The above equation shows that the direction of acceleration is the same as the direction of your change in velocity. We're going to see exactly what that means here in just a second. All right, so what is your change in velocity? Your change in velocity is always going to be your final minus your initial velocity. Here, your VF is the final velocity, VI is the initial velocity. Then for example, we're going to use two vectors, your initial and your final velocities. Notice that your initial is larger than your final. That should tell you that we're going to be going through some negative acceleration. We're slowing down. So when you add them together, or actually subtract them, we're going to take V plus a minus VI, so VF minus a VI. Whenever you subtract the initial velocity from the final velocity, you need to flip it 180 degrees. Now using your tip-to-tail method, your resultant is going to be the vector that goes from where you began and ends at where you ended. Here's your delta V. Now notice the direction it points, which makes sense because you were slowing down. So the acceleration points in the opposite direction because delta V points in the opposite direction. Remember, acceleration equals your change in velocity over your change in time. Now, what if we wanted to compare how fast something is going at 2 different times? But we can't use the motion sensor because its path is curved. Because remember, the motion sensor only detects direction straight in front of it. So if it's something that's curved, the motion detector is not going to work. Or remember the strobe photo where they would drop a ball or roll a ball and you would took a bunch of different pictures and then superimposed them on top of each other? That is kind of where we're going to go. You could compare how fast the ball was going at 2 different times by looking at the distance between the photos. So if the photos had bigger distance between the balls, then you know that they were going faster. If they were closer together, you know that it was going slower. Now, what if instead of using a strobe light, we used a flashing LED? And here, we're going to call this a blinky. And I did not come up with that name. That somebody else did. And took extended exposures of the photo in the dark. Well, we're going to see what we can do. Here we have the flashing green LED. This is going to be a pendulum that you're going to see in lab. And notice how you can see it go around in kind of an oval shape there. And some unlucky person is standing right above it looking down at the camera. Anyhow, so you can see what the picture looks like initially. Then after we take the picture, we turn it to a grayscale and then into a negative, it gives us this much nicer looking picture that we can deal with. Now notice each of those lines, the longer the line, the faster it's going. The slower the line, the slower it's going. Okay, so here we have another Blinky photo. And it looks like the Blinky is moving along a track of some sort. So you see it's going slow at the top, and it speeds up as it goes down towards the bottom, and then slows back down as it gets back towards the top on the, I'll assume that it's moving from left to right. Now here we have some sets of vectors. So we have vector set A, vector set B, and vector set C. Now notice these vectors, whenever you draw them, because you're going to be doing this exact same thing that we're doing here. Whenever you draw the vectors, it's going to be from the tip of the dash to the tail of the dash. So if it's curved, your vector is not going to be going exactly along. It's not going to follow the Blinky exactly. It's going to go draw your vector from the beginning to the end of the dash. And let's see here. The blue lines, of course, are your initial, and the orange vectors are the final velocity. So there's your initial and your final. Now, whatever we do, your initial minus your final, you're going to take your initial, then you're going to subtract your final, and your delta V is going to be the line that goes from where you started to where you end. All right, so some things to think about before we go is, what does the length of a vector signify? What does it mean when you have a longer or a shorter vector? How do you add and subtract vectors? Because you're going to be doing a lot of that in this next lab. So how do you add them? How do you subtract them? What does acceleration, how does acceleration affect velocity when they're in the same direction or when they're in opposite directions? What happens to the velocity? Think about those relationships, because that is actually probably the main focus of this lab. All right, guys, well, have fun, and we'll see you next week.